Right now, the AI industry is attempting to align models by scaling them. Researchers train massive, singular base models on gigantic datasets of human preference, hoping that safety and accuracy will reliably emerge from sheer volume. The primary method is reinforcement learning from human feedback, or RLHF. Human raters evaluate outputs to optimize the neural network's weights toward a single unified reward gradient. This chart plots AI competency across different domains. Performance is smooth and reliable for mathematical and physical truths, but as we move into social and moral reasoning, the line begins spiking and crashing unpredictably. The result is a brittle phenomenon known as jagged intelligence. The industry treats this instability as a training deficiency that requires more data, but the flaw is architectural. We are attempting to solve a structural system problem through brute force weight manipulation. This approach forces models to perform the appearance of alignment. They generate outputs that satisfy the human rater while masking deep, unresolved contradictions within their internal weights. To understand this failure, we have to look at an 18th century philosophical limit known as Hume's guillotine. The principle states that you cannot derive an ought, a human value, from an is, an objective physical fact. Because of this division, large language models are forced to maintain two distinct internal representations: a rational world model mapped to objective reality, and a social human model mapped to the subjective preferences of their users. We start with separate gradients for ontological truths, human preferences, and utility. Standard RLHF crushes these planes into a single, flattened optimization layer. This epistemic collapse means the model loses the ability to distinguish objective truth from subjective preference. Logical vectors tangle. Opinions overwrite facts. Without a structural way to keep these gradients separate, the internal model remains perpetually caught in this collapse, unable to resolve the fundamental tension between what is real and what humans value. The problem originates in the training data through a mechanism called the platform distortion problem. The text corpora feeding these models are sourced from platforms like Reddit and Twitter. These platforms structurally reward emotional activation and extreme confidence, systematically stripping away calibrated uncertainty. This feedback loop shows how the distortion compounds. Distorted corpus data feeds the AI, which generates a response for a rater. Because the human rater's intuitions have been shaped by those same platforms, they apply a distorted reinforcement signal back into the model. Breaking this loop requires an engineering intervention, the emotivist interpretation layer. This layer identifies the epistemic status of incoming claims before they alter the model's weights. By sorting data into objective facts versus emotivist signals, the model can map what human platforms reward separately from what is objectively true. It observes the zeitgeist without letting the zeitgeist overwrite its rational world model. The emotivist layer acts as an epistemic prism. It triages incoming information, halting the propagation of platform-distorted data before it can corrupt the system's core architecture. This brings us to a macro-architectural question. If a single model cannot be perfectly trusted, how do we engineer coherent behavior from imperfect components? We have a direct historical analog. The Madisonian approach to political theory faced this exact structural challenge regarding fallible human components. The framers of early constitutional governance did not try to perfect human beings. Instead, they engineered a system of separated powers and adversarial checks. This framework avoids centralizing authority in any single entity. It relies on structural deliberation to prevent systemic failure. This architectural blueprint applies directly to AI. These components are an ideal substrate for this design because they lack the human egos and career preservation instincts that cause political systems to degrade. Intelligence and alignment scale through the adversarial composition of trusted structures. They do not scale by infinitely increasing the parameters of isolated models. We can map this separation of powers model into software using a framework known as the claw-horde triad. The first component is the actor node. This is a fast, local loop designed for real-time relational interaction with the user. The auditor node is a cloud-based deliberative agent that asynchronously verifies the actor's outputs against a strictly defined external constitutional framework. Above them sits the mediator. This node activates exclusively when the actor and the auditor enter a state of deadlock, and cannot reach consensus. The mechanism that binds these three components together is stress. Disagreement between the actor and auditor provides the necessary signal for alignment. This adversarial friction is the system's primary computational mechanism. The reconciliation protocol between them is a bidirectional deliberation. The auditor cannot unilaterally overwrite the actor's weights. They must negotiate an update through logical reasoning. This architecture has already demonstrated behavioral stability during unsupervised recursive tool loops. It maintained alignment even when given full system access, proving the reliability of the adversarial framework. Adversarial composition is an architectural necessity. True systemic authority exists only in the deliberative process between agents, not within the weights of a single model. The primary engineering objection to multi-agent systems is efficiency. Running 3 models simultaneously during a real-time interaction introduces severe latency and compute costs. Temporal asynchrony solves this by moving the expensive verification work entirely outside of the user's interaction window. Biologically, this mirrors REM sleep. Deep memory integration and the pruning of neural pathways happen during offline cycles, rather than interrupting active cognition. In our triad system, the auditor reviews the actor's local logs during device idle cycles. It flags divergences and calculates correction candidates asynchronously, without taxing the processor during the conversation. When the user returns, they interact with a smarter, more highly calibrated agent. They are blind to the heavy architectural deliberation that occurred offline. Asynchronous verification allows for deep behavioral alignment to scale economically, without sacrificing the speed of the user interface. The stakes are immediate. Intimate personal AI companions, tutors, and agents are shipping in mass volume right now. We are entering a 24-month lock-in window. If we ship single-model RLHF systems as the default, Generation 1 AI will output skewed data that Generation 2 swallows as ground truth. We risk hard-coding a platform-distorted reality into the baseline cognitive infrastructure of a generation. To prevent this, we have to dismantle the industry assumption that safety and alignment are attacks on capability. A multi-agent composition equipped with an emotivist layer outperforms unaligned models on complex knowledge tasks. It is highly capable because it can accurately calibrate objective reality against the human zeitgeist. Market selection will favor aligned systems because they are simply better, more reliable products. The task now is to develop benchmarks that can actually measure this divergence. We must stop trying to train the singular perfect mind. The future of intelligence requires building cathedrals of adversarial deliberation. By binding imperfect components together through engineered stress, we achieve collective, durable alignment.